In this section, we're going to learn about the chain rule for multivariable functions. Now, before we jump right into the multivariate case, I want to very briefly review the single variable chain rule just so we have a foundation to build upon. Okay, so in the single variable case, the idea is I have some function f, and instead of just plugging in x, I'm plugging in some other function dependent upon some other variable. And then I take the derivative with respect to that innermost variable. The chain rule gives us a way to evaluate this derivative piece by piece. We first take the derivative of the outermost function with respect to the first variable inside f. We kind of ignore the t at the beginning. We take the derivative of f with respect to the x, and then we give the x its term. We take the derivative of x with respect to t. And by taking it in turns, we can take the derivative using the chain rule. Okay? Now, in the multivariable case, what are we doing? The idea here is we have a function of two variables. And instead of just plugging in an x value and a y value, we plug in two functions, one for each component. And then we take the derivative of this with respect to t. Okay? So let's derive a formula for the multivariable chain rule. Now, a little bit of a warning, this is a little bit notationally heavy, so I'll try to move quickly. I hope, though, that you'll focus more on the concepts rather than on the notation. Okay? So this is just a single variable derivative, right? There's only one variable here that I'm differentiating, just the t. So I'm just going to use the usual way we define a derivative. I'm going to evaluate the function at t plus h, and then subtract the function evaluated at t. That lets us see how the function changes as we change the value of t. And we divide it all by h. All right? Now, in order to make this work, I want to split it up. I want to break it down as much as I can, because right now there is a lot going on. I'm plugging into function x, I'm plugging into function y. Both the x and the y are changing. And then I plug those changes into function f. What I want to do is I want to focus at one change at a time. Okay? So we're going to need some room here. So what I'm going to do, I'm going to split this into multiple fractions. Okay? So I'm going to start with this that we already have, but instead of allowing both x and y to change at the same time, I'm going to leave one of them fixed. Let's leave the y fixed. Okay? So I'm going to include a new term, minus f of x of t. I'm letting the x function change, and then I'll leave y the same. Okay? Now I can't just add things in willy-nilly, right? And this doesn't change into this. I can't do that. So what I need to do is, if I'm adding a negative one of these in, I also have to add a positive one in to balance it out. Okay? Notice that I really haven't changed anything, right? I've subtracted this, I've added this in. they're exactly the same thing, so they cancel out. But by adding both of these in, it allows me to focus on the change on this side, just the change in x, right? I go from x of t to x of t plus h while leaving y of t plus h constant, right? And over here, I'm doing it the other way around. The x is staying the same in both these function evaluations, but the y changes. I go from y of t to y of t plus h. And that allows me to focus on just how the x is changing over here and just how the y is changing over here. Okay? But there's still too much going on because not only is the x changing, the x is changing in response to the change in t. So I want to break this down further so that I focus on just the change in x and just the change in t. Okay, so what I'm going to do, this is going to get quite long. I'm going to leave the numerator the same. Okay, but what I want to do is I'm going to divide, instead of by h is how much t is changing, right? I'm going from t to t plus h, so that is a change of h. Instead of focusing on the change of t down here, I'm going to focus on the change in x. So I'm going from x of t to x of t plus h. So that would be x of t plus h minus x of t. Okay? Now again, I can't just throw this in willy-nilly just because I feel like it, just because it looks nice. So if I'm going to divide by this, and let me actually change the color so you can see what's being added. If I'm going to divide by this, I have to keep things balanced by also multiplying by it. Okay, and that h I've just moved over here. Okay, so this first fraction I've split into these two pieces, right? Why? Because here I'm focusing on the change in x. This is how much the x changes. And so I'm saying how much does the function change, the function f change, as the x value changes, okay? And then separately over here, how much does the x change as the t value changes? Remember, h is t plus h minus t. It's how much the t has changed. Okay, so I'm focusing on the changes differently. And then I want to do the exact same thing over here, but just with the y's. All right, so let me scooch on over. I get f of x of t, comma y of t plus h, minus f of x of t y of t. So I haven't changed the numerator at all. The change is coming down here in the denominator. Instead of looking at h down here, I'm going to look at how y changes. So y of t plus h minus y of t. And since I'm dividing by this, I have to keep things balanced. I have to multiply by it also. And I'll put this h right here in the denominator of this second fraction. Okay? So a lot of symbols, but we're almost done. Right? Because now, what are we looking at? We're looking at how much f changes as the x changes. And since h is going to 0, this is going to 0 also, right? X of t plus h, as h gets closer to 0, this becomes more and more like x of t. And since this is becoming more and more like x of t, this is becoming closer and closer to 0. So what I'm doing is this is effectively the derivative of function f with respect to variable x, with respect to variable x, while leaving the y constant. Okay, so when I take the limit, in the limit, this becomes the partial derivative of f with respect to x. I'm seeing how f is changing as x changes. Okay. Similarly over here, this is just a classic derivative. If I take the limit as h goes to 0, I'm seeing how much the x changes as the t changes. This is the derivative of x with respect to variable t. The derivative of x with respect to variable t. Okay? And then similarly over here, I'm looking at how the f changes, how we go from here to here. What's the change in f? As I moved the y, as I changed the y value from here to here. So that's going to be the partial derivative of f with respect to y. And then finally, this last fraction, I'm looking at how the y function changed as we changed the t value, as we went from t to t plus h and moved that h units over. Okay, as we let h go to 0, this becomes the derivative. So in the limit, it becomes the derivative of y with respect to t. And that is our formula for the multivariable chain rule in 2 variables. In 3 variables, obviously I didn't want to write it because this is already long enough, but in 3 variables, we would just have the partial derivative of f with respect to z times dz dt. Okay. So let's summarize. The chain rule in 2 variables. The derivative with respect to t of f of x of t comma y of t is equal to partial f partial x, derivative of x with respect to t, plus partial f partial y, derivative of y with respect to t. Okay, now that's kind of a bit of a mouthful, isn't it? It's not as simple as our single variable chain rule up here. And I think there'd be a fair few students who'd say the single variable chain rule isn't simple either. So is there an easier way to remember this multivariable chain rule? Actually, there is. If we look at it long enough, we might see that this looks a lot like a dot product. Okay, it looks a lot like the derivative of f with respect to x, comma, derivative of f with respect to y, dotted with the vector with the partial derivative of the derivative of x with respect to t and the derivative of y with respect to t. Okay. So it's just a dot product, and this, we have a special name for this vector, right? The vector of partial derivatives, we call it the gradient. And here, if we are treating this not as 2 distinct functions, but as one vector valued function, then this would be the derivative of that vector valued function. Okay? So instead of thinking about this as x of t and y of t separately, we could think about this as a vector valued function r of t with components x of t and y of t. And so then this would just be the derivative of those 2 components. It'd be the derivative of our vector valued function. Okay. So another way to write this is that if I am taking the derivative of some function and I'm plugging in a vector valued function into it, then the chain rule just says I'm going to take the gradient of the outermost function, the vector of partial derivatives, and I'm going to take the dot product of that with the derivative of the vector valued function I'm plugging in. This rule isn't limited to just two variables, this is actually a general way to write the multivariate chain rule. Whether you have a vector valued function of 2 variables or 3 variables or 10 variables, this will always be the way we express that multivariate chain rule. Let's take a look at an example. So here we have a function f of xy equals negative 9e to the x sine of y. But x and y we are going to treat as functions of t. So we want to find the derivative of f with respect to that variable t in two different ways. Now we're first going to use that multivariate chain rule, and then we're going to do direct substitution. Both ways should produce the same result. Okay, so let's use the chain rule first. Okay, so here, these are our two components. So if we're thinking of a vector valued function, our r of t would be the x component is t squared, the y component is 7 pi t. And what we want to do is we want to plug the x and y components into the x and y of the function. We want to take the derivative of plugging the x and y components into the function. We want to take the derivative of plugging that vector valued function into f. Okay, now according to the chain rule, this should be equal to the gradient of f, and then we take the dot product of that with the derivative of r prime of t. Okay, so let's separately find the gradient of f, and then r prime of t, and then we can put it together. Okay, so let's start with the gradient of f. So the gradient of f is going to be the vector of partial derivatives. The partial derivative of f with respect to x would be, well, this is the only variable that we wouldn't treat as a constant, and the derivative of e to the x is e to the x. So actually we get exactly the same thing as we start with. The negative 9, the sine y, we treat as a constant, and then the derivative of e to the x is e to the x. Okay. Now the partial derivative of the function with respect to y, negative 9 e to the x we're treating as a constant, so it'll come along for the ride. We just take the derivative of sine of y with respect to variable y. Derivative of sine of y is cosine of y. Okay. And then finally, and although I don't write it here because it makes things a little bit busy, we want to plug the x and y values, the functions in terms of t, into x and y here. Our final answer should be in terms of just our derivative variable t. Okay, so let's plug in r of t. So every time I see x, I'm going to plug in t squared instead. Every time I see y, I'll plug in 7 pi t. Okay, so my gradient of f evaluated along the function r of t will be negative 9 e to the t squared sine 7 pi t. And then this one will be negative 9 e to the t squared cosine 7 pi t. Okay, so this first bit is done. We have the gradient of f evaluated along our vector valued function. Now we just need the derivative of that vector valued function. So now let's take the derivative, r prime of t. So just the derivative of these two components. Derivative of the first component is 2t. The derivative of the second component is 7 pi. Okay, we have the pieces. Now we just need to take the dot product. Okay, so plug in gradient of f, negative 9 e to the t squared sine of 7 pi t, comma, negative 9 e to the t squared cosine 7 pi t. And then I'll take the dot product of that with r prime, which is 2t comma 7 pi. So I'm going to multiply first component with first component. Okay. And I'm going to simplify as I go. So if I multiply the 2t by this, the negative 9 times the 2 is negative 18. I'm going to put the t right here, and then all of this right here. E to the t squared sine 7 pi t. So that's my first component with first component multiplied together. Now same thing, second component times second component. 7 times negative 9 is negative 63. Then I've got the pi, and then e to the t squared cosine of 7 pi t. And that is the derivative of f of r of t with respect to t. Okay, we used the chain rule, we found the answer. Okay? All right, we do have to do this one other way. We need to do this with direct substitution. You may be asking, why are we going through all this work when I could just plug these in and then take the derivative after I plug them in? And you're right, we can do that. Okay, so let me just write down my functions just for reference. So f of xy was negative 90 to the x sine of y. My two component functions, the x component was t squared, the y component was 7 pi t. And now let's directly substitute this function into this one. Okay, so I will plug in t squared into this. So I get e to the t squared, and I plug in 7 pi t into y. So sine of 7 pi t. All right, now I have a function of t. I want to take the derivative of this function. So derivative of f of r of t. I will need a product rule here because I have this function multiplied by that function. Okay, so I get e negative 9. Derivative of e to the t squared is e to the t squared times 2t by the chain rule. And then 7 pi t I'm going to leave as is for now. Right, so I took the derivative of this guy, left this guy unchanged. Now swap. Okay. Now leave this guy unchanged, so e to the t squared, and take the derivative of sine of 7 pi t. Derivative of sine of 7 pi t is cosine of 7 pi t times the derivative of the inside. Derivative of 7 pi t is just 7 pi. So if I fully simplify, I get negative 18t e to the t squared sine 7 pi t. And then multiply that 7 pi by the 9 here. I get negative 63 pi e to the t squared cosine 7 pi t. And the two derivatives do indeed agree. Now, which one seemed easier? It did seem like we had to think a little bit harder and write a little bit more for the chain rule. Direct substitution seemed a little bit easier. Why are we even learning this if direct substitution is just easier? Very rarely will we use direct substitution to take a derivative of a problem like this. If we have a problem like this, we will usually use the direct substitution method. The chain rule is still an important technique, but it is usually a technique that we use to develop the theory. It is a good way to separate the derivative of f and the derivative of r when we don't have a concrete function f or a concrete function r to work with. If we're trying to find a pattern, then the chain rule will help us do that when we have a more abstract situation, when we can't simply directly substitute. Let's take a look at another example where direct substitution isn't an option. So here I want to find the derivative of function h with these two components that depend on t plugged in. Now I do know that the gradient of h at 0.30 is equal to -1.5, but notice I don't know what function h is, right? It doesn't tell me what function h is, so I can't just directly substitute in the components and just take the derivative of t. I need the multivariable chain rule here, okay? So let's make sure we understand what we're doing here. These two components, that's my vector valued function. So r of t is equal to 2t plus 3, first component, and then t squared minus 4t is the second component. Okay, now what I want to do is I want to plug that into my function h, and then take the derivative of that with respect to that innermost variable t. Now here's where we use the chain rule. According to the chain rule, this is going to be the gradient of function h evaluated at r of t. Maybe I'll write it just to be clear. And then I take the dot product of that with the derivative of r of t. Okay. Now, that's the formula to find the derivative. But I don't care about the derivative anywhere. I care about the derivative specifically when t is equal to 0. Okay, so if I'm interested when t is equal to 0, I want to evaluate this when t is equal to 0, then I can plug 0 in here and see what we get. Okay, now for this one, let's first find out what r of 0 is. So if I plug in 0 into this function, I will get 3, 0, right? So I want the gradient of h at 3, 0. Just taking this and plugging it in. Okay, and then here I want r prime of 0, so I'm going to need r prime, aren't I? So let's take the derivative of my function r here. R prime of t, I just get 2, 2t minus 4. If I plug 0 in, I get 2, -4. So that's what this is. Dotted with 2, -4. Okay, and now comes that extra piece of information we have. They did tell us what the gradient of h is at the point 3, 0. It's -1.5. So if I plug that in, then I just have a dot product. And so I get -1 times 2, that's -2, plus 5 times -4, that's -20. So my final answer here is -22. That will be the derivative of h of r of t with respect to variable t evaluated at t equals 0. Sometimes the vector valued functions we're plugging in are functions of more than one variable. Okay? Maybe instead of just being a function of t, maybe it's a function of two variables, u and v. In this case, the chain rule is essentially the same. We just have two possible derivatives. The derivative with respect to u and the derivative with respect to v. So, for example, if I'm plugging in this two variable vector valued function into another function f, and I want the partial derivative of this composite function with respect to u, I still use the chain rule. I still first take the gradient of function f, and then take the dot product of that with the derivative of the vector valued function. The only difference is now there are two variables I can take the derivative with respect to. I take the derivative, obviously, with respect to variable u. So the derivative of r with respect to u. And similarly, partial derivative of f with respect to v will be the gradient of f dotted with the partial derivative of r with respect to variable v. Okay, notice the gradient will be the same in both cases. Okay, let's take a look at an example. So here we have a function w. It is a function of both x and y. But x and y are themselves functions of other variables, functions of u and v. We want to find the partial derivative of w with respect to u and the partial derivative of w with respect to v. Okay? So in this case, our vector valued function, r of u of v, first component is the negative 3u plus v. The second component is the u minus 4v. And I'm plugging that in to vector w here. So I have w of r of u and v. Okay? So we want to find the derivative of w with respect to u, the partial derivative of w with respect to v. So let's do that using the chain rule. This is another situation where we could do it with substitution. And substitution actually would probably be the easier method. But let's do it with the chain rule, and then you can confirm on your own that substitution will give us the same answer. Okay? So let's take the partial derivative with respect to u. According to the chain rule, we would want the gradient of w first, and then plug in our vector valued function into that gradient, and then take the dot product of the partial derivative of r with respect to variable u. Okay? All right, so let's take the gradient first. Gradient of w. If I just take the gradient, partial derivative with respect to x is 10x. Right? Partial derivative with respect to y is 4y. And so the gradient is just the vector of those partial derivatives. Okay? Now I want that gradient evaluated along the vector valued function. So I'm going to plug in the vector valued function. So in place of x, I plug in negative 3u plus v. In place of y, I plug in u minus 4v. So 4u minus 4v. Okay, that will be the first term, my first factor here, in this dot product. Okay, the other one I need is the partial derivative of this vector valued function with respect to variable u. Okay, so partial derivative of r with respect to variable u. For the first component, that's just negative 3. Partial derivative of the second component with respect to u is just 1. Okay, so now I could plug these in. Let's plug in this first guy. 10 times negative 3u plus v, comma 4u minus 4v. Then I'm going to take the dot product of that with this, negative 3, 1. And I'm going to get, let me kind of visually separate these. I'm going to get first component times first component. That negative 3 will multiply this 10, and I'll get negative 30 times negative 3u plus v. And then second component times second component, I'll get 1 times this, which will just leave this the same. So plus 4u minus 4v. Okay? And that is the answer. We can simplify further, but I'm going to leave it there. Okay? If you wanted to, you can distribute and then combine your like terms. All right. So we found one of the partial derivatives. Let's now find the other one. Okay, so to find the partial derivative of w with respect to variable v, we again need the gradient of w. And we're going to take the dot product of that with the partial derivative of r with respect to variable v. Okay. Now notice gradient of w, we've already calculated that. The same gradient. Okay. The only difference is now we need the partial derivative of r with respect to v instead of with respect to u. So let's take the partial derivative of function r with respect to v. Partial derivative of r with respect to v. My first component, partial derivative with respect to v is just 1. Second component, my partial derivative with respect to v is -4. Okay? So I'm going to get the gradient of w evaluated along the vector valued function. That's this guy right here. So that's 10 times -3u plus v. And then the second component of that is 4 times u minus 4v. I'm going to take the dot product of that with the partial derivative of r with respect to v, which is just 1 -4. So if I multiply corresponding components and add them together, 10 -3u plus v times 1 is 10 times -3u plus v. And then 4 times u minus 4v times -4 is going to be -16 u minus 4v. Okay. Again, we could simplify by distributing and combining like terms. You can do that if you wish. I'm going to leave it there. We've done the most important part. Let's take a look at just one more example. Here is another example where we cannot solve this using direct substitution. We do not have enough information. We do not know exactly what function g is. We have to use the chain rule for this problem. So we know that the gradient of g at some particular point gives us 1, 0. Okay? We want to find the partial derivative of a function g with respect to u, and we want to find the partial derivative of function g with respect to v, both at the particular point where u and v is equal to -2, 2. Okay. So what we're plugging in here, that's our vector valued function. So it's a vector valued function of two variables, of u and v. The first component that we plug in is 3u minus eu plus v. And the second component we plug in is 1 over u minus v. Okay? So for the partial derivative of g with respect to u, according to the chain rule, we're going to take the gradient of g and then take the dot product of that with the partial derivative of r with respect to u. Okay, and similarly, we want the partial derivative of g with respect to v. We're going to take the gradient of g and take the partial derivative of that of r with respect to v. Okay. Now for both of these, if we want to find these, we're going to need the gradient of g, and we're going to need the partial derivative of r with respect to u and with respect to v. So let's see what we could do about those. Okay. Now gradient of g, I cannot find exactly because I don't know what function g is. Fortunately, I don't need to know. I'm only interested in these partial derivatives at particular points, right? But I can find the partial derivative of r with respect to u and the partial derivative of r with respect to v at the point of interest when uv is equal to -2, 2. Okay, so let's calculate those. Partial derivative of r with respect to u my first component, partial derivative with respect to u, I get 3. And then derivative of e to the u plus v would just be e to the u plus v. And then if you multiply by the derivative of the exponent, you just get 1. Okay? And then for this one, the easiest way to approach this is to think of this as u minus v to the negative 1. That way you don't have to pull out a quotient rule. Okay? You just need a power rule with a chain rule. So I get negative u minus v to the negative 2, and then multiply by the derivative of the inside. The derivative of u minus v with respect to u would just be 1. So I don't have to multiply by anything. Okay? And I'll just tidy this up in place. That negative 2 power, the negative means it's going to the denominator, the 2 means it's squared. So if I were to tidy this all up, I get negative 1 over u minus v squared. Okay? Now what I want, I don't just want this. I want this evaluated at negative 2, 2. So now let's plug that in. I plug in negative 2, 2. The 3 is a 3. U plus v, that'd be negative 2 plus 2. That'd be e to the power of 0. E to the power of 0 is 1. So I'm going to get 3 minus 1. That's going to be 2. And then over here, I get u minus v. U is negative 2. V is 2. So that's negative 2 minus 2. That's going to be negative 4. Squared is 16. So I get negative 1/16. Okay? So that's what I'm going to use to calculate this partial derivative when u and v is negative 2, 2. All right, let's calculate this guy next. Partial derivative of r with respect to v. Derivative of 3u, we treat as a constant. Derivative of a constant 0, so it goes away. Derivative of negative e to the u plus v would be negative e to the u plus v. Technically, you need a chain rule there, but the derivative of u plus v with respect to v would just be 1. Okay? And then the derivative of 1 over u minus v, we're again going to think about it as negative, or u minus v to the negative 1 power. So negative 1 times u minus v to the negative 2 power, and then multiply by the derivative of the inside. Derivative of u minus v with respect to v would be negative 1. So if I simplify that, the negatives will cancel, right? Negatives become positive, and u minus v to the negative 2 becomes 1 over u minus v to the positive 2. So I end up with positive 1 over u minus v squared. Okay? Now what I want is I want to know how these guys will evaluate at the particular value uv equals negative 2, 2. So plug in. Negative 2, 2 is, if I plug in here, negative 2 plus 2 is 0. E to the 0 is 1, so I'm going to get negative 1 for that first component. And for the second component, negative 2 minus 2 is negative 4. Squared is 16, so I get 1/16. Okay? So I know what I'm going to plug in here and here. I still need to figure out what I'm plugging in here and here, right? Now I can't find the gradient of g, but I do know something. I know the gradient of g at negative 7 comma negative 1/4 is 1, 0. So maybe whoever wrote this problem chose this particular value and chose these values so that we do know the gradient of g where we need to. Okay? So specifically note that r of negative 2, 2, the point here, is equal to, so negative 2 plus 2 is 0, so that's just 1 there. And then 3 times negative 2 is negative 6. So negative 6 minus 1 is negative 7. And then 1 over u minus v. U is negative 2 minus v of 2. So that's 1 over negative 4. That's negative 1/4. And look at that. -7 comma -1/4. It matches. Okay. So we know that the gradient of g, put it over here, gradient of g at r of -2, 2 is equal to, according to this, 1, 0. Okay, and that's all the pieces that I need. Okay, so now let's plug in. What we want is the partial derivative with respect to u of g of r of uv evaluated at uv equals -2, 2. So that's going to be the gradient of g of r of -2, 2 dotted with the partial derivative of r with respect to u at -2, 2. I have both of these pieces. Gradient of g at that point is 1, 0. Dotted with the partial derivative of r with respect to u at the point -2, 2. That's 2, -1/16. And if I take the dot product of those, I'll just end up with 2. That's the partial derivative of g with respect to variable u at the value uv equals -2, 2. Just one more derivative to go. We need the partial derivative of g with respect to variable v at that point. So the partial derivative of g of r of u of v with respect to variable v evaluated at where u and v is equal to -2, 2 is equal to the gradient of g of r of -2, 2 dotted with the partial derivative of r with respect to v at -2, 2. Okay, we have the pieces. Gradient of g at the point is 1, 0. And the partial derivative of r with respect to v at the point is 1, 1/16. Take the dot product. First component times first component is 1. Second component times second component is 0. I just get 1. And so I have both my partial derivatives at the point uv equals -2, 2.